Hello everyone. In this video, we're going to actually formally introduce how we are going to solve these sort of problems using our shortest path algorithm. We're then going to compare it to our minimum spanning tree algorithm on the same graph. So just to make sure that we do that correctly, I'm going to begin by copying this graph so we have several copies of it for the future. So let's copy it. And we'll paste it later when we need it again. So let's perform our algorithm. We're going to always make greedy decisions. We start by adding some node to the graph. I'm going to add this far left node to the graph. We're then going to look for the cheapest node adjacent to that node. So the cheapest node adjacent is going to be this path up here that has a cost of 7. The cost of starting here at the first node would be 0. Oh, let's do this in not red. Let's do it in green. The cost of this node is 7. Now that we've added it, the cost of adding this node down here would be 8. And the cost of every other node, like what we did with the minimum spanning tree algorithm, is going to be infinity. So let's then add the next, once we add in that next node that has a cost of 7, we're then going to check everything adjacent and potentially update costs. The cost of going down from that node would be 9. The cost of going to the right would be 11, which last time I checked was better than infinity. And the cost of going down into the right would be 15, which again is better than infinity. We then look at all of the costs and find the cheapest one. The cheapest of the costs would be 8. So the best way to go would be here, down to that node. We then update the cost of every white node adjacent. Going up and to the right from that node would be a cost of 15. Don't need to update it, it's not better. Going down and to the right would be a cost of 12, 8 plus 4. So this would update this cost to 12. We then look at all of the costs, 11, 15, and 12, and then infinities, and add the best one. The best of those would be 11. We add it, and then look at every single adjacent node. The adjacent nodes here are going to be this one along the top that has a cost of 19 now. Then down, which has a cost of 11 plus 4, which is not better than the current cost of that node. We then look at the cost of all of our nodes, which are 19, 15, and 12, and choose the best of those. Best of those is 12, so we add that. And then update the cost of the adjacent nodes. 12 plus 2, that's going to give me a cost of 14. That's a better cost. 12 plus 3, that's a cost of 15. 12 plus 5, that's a cost of 17. We then add the best of them. We have 19, 14, 15, 17. Best one is 14. Sorry, let's shade in this node we just added. Now we added that node. We then update everything adjacent. Well, we have this node over here that we've never seen before. That has a cost of 21 now. This node down and to the right has a cost of 18. That's not better. So we then choose the best among the bunch. 19, 21, 15, 17. 21 wins that battle. Sorry, 15 wins that battle. So then we add that to our shortest path tree and update everything adjacent. If we were to go up from here, we don't have that edge, so don't listen to me. Because I didn't give it a weight. If we were to go right from here, we would get a cost of 20. And that's not a place we can go. So then let's look at our costs. We have 19, 21, 20, 17. 17 wins that fight. We then add it to the graph and update everything adjacent. 17 plus 4 gives me 21. That doesn't win. We then look at the costs. 19, 21, 20. 19 wins that. Oops, sorry, we don't X out 19. We then look at everything adjacent to that node we just added. We could do 19 plus 2, which is 21, doesn't beat 21. 19 plus 6, 25 does beat infinity. And that's it. Now, we are going to check the cost. 25, 21, 27, and that is it. We have 20. That wins that fight. So we add it to the shortest path tree, and then update everything adjacent. We have 20 plus 2 is 22. That doesn't win. But 20 plus 6, that does beat infinity. So then we have 21, 25, and 26. Winner of that bout is 21. Add it to the graph. And then check everything adjacent. We could go 21 plus 3 is 24. So that wins. 21 plus 8 is 29. That doesn't win. We then have 24 and 26. So we're going to add the 24 to the graph. We then only have one. Then we have one adjacent node. 28 doesn't beat 26. And then we add 26 via this bottom path. And shade. And now we've created a shortest path tree, visualized with the purple nodes and the purple edges. That is a different tree than the minimum spanning tree, which we'll do in a second. And the way we're doing this is by storing at each node the cost of getting there from the start. So once we're done here, not only do we have the shortest paths, we also have the cost of the shortest paths for every single node in the graph, which is very useful for reusing this information if possible. So let us try to analyze the minimum spanning tree for this graph and see how it compares. So let's paste the minimum spanning tree here. For the minimum spanning tree, let's do this in a different color just to emphasize the difference. I would start somewhere over here. I then choose the best path to any non-orange node. I then choose the best path to any non-orange node. I have 8, 2, 8, 8, and 4. 2 wins that. I then have 4, 8, 7, 4. So I choose 4. I then have 8, 4, 8, 7, and 4. So I choose one of the 4s. I then have 8, 7, 4, 4. I choose one of the 4s. I then have 8. Oh, I still have this extra edge I didn't mean to have. I have 8. I have 7. I have 2. Oh, sorry, I should have chosen this 2 last time. Don't listen to me. And we got rid of this. I apologize. 2 was the winner, so we added that node. The winner now is going to be 3. Going up this way. We then check. We have 5. We have 5. We have 7. And we have 8. So the winner of that is one of the 5s. So we add that one to the graph. Then I need to add this node. 4 is going to beat all of the other options because 5 was the best. I then have 2 here as an option. I then have another 2 as an option, which is the best weight in the graph, so that's for sure got to be the winner. I then have 6, 8, 3, and 6. 3 wins that fight. And then I have 4 as my best way to get to the final node. Notice this looks substantially different than the shortest path tree. So if we zoom out, it looks substantially different. There are several edges that are used in one but not in the other. So, for example, to get to the node on the far right, we use the top edge versus the bottom edge. We also used the edge down from node, from the node in the top. We have this sort of long bracket going here, and the bottom part of the graph also looks different. So these are going to be different. The minimum spanning tree and the shortest path tree will be different. Or could be different. They could be the same as well. So this is a comparison of the two, but the idea is the same. We're always looking for the best thing that we have not added yet. Just what we mean by best thing is going to be different. We're again making a greedy choice along the way of always choosing the next best node to add. Just what we mean by best will be adapted. And therefore, our code for the algorithm will end up being very similar, as we will see shortly. But that is it for discussing the actual algorithm and how you might perform it. I would recommend keeping track of the cost when you're actually using this algorithm by hand.